Thanks for the introduction. I'm Zeying. Today I will talk about NetMigrate, an in-memory key-value store line migration system. This is a joint work with Yibo and my advisor, Professor Alan Liu. In-memory key-value stores are widely used by modern internet services, such as future store of machine learning inference, in-memory caching, and real-time analytics. And it can scale to billions of records in a distributed manner, and can require to retrieve millions of records under low latency constraints. In distributed key-value store systems, data are sharded and can be reconfigured over time. Line migration promises no service downtime during the key-value store shard migration from one node to another, and thus it can meet the service level agreement. So why we migrate the data? It can provide the load balancing to fit the dynamic and skewed workloads. For example, there are hot items A and B, and both of them are in the server 1. And server 1 is overloaded because of a lot of queries going to it. If we can migrate the item B to another server, then the query can shift to server 2. We can achieve the load balancing among them. Migration can also happen to improve the spatial locality and thus enhance the access throughput to the backend server. Also, it can happen when there's a cluster horizontal scaling or hardware upgrades. Existing solutions of line migration can be divided into 3 categories based on which node serves the query during migration. They are the source-based migration, destination-based one, and hybrid. Source-based migration uses the source node to serve both read and write requests. However, a write request can update a value that this key-value pair has already been migrated to the destination. And then destination will have the stale value. So source-based protocol, they collect and migrate the dirty data log of this updated value and migrate them to the destination server. So finally, destination will have the updated value. It can have a relatively low query latency during migration because source node already has all the queried data. However, it will transfer the extra dirty data from source to destination. And also, it can have downtime when terminating the migration because the source node has to be frozen and don't do the write request to migrate the last piece of the dirty data log. Destination-based migration uses the destination node to serve all read-write requests, and it shifts the data ownership to the destination at the beginning of migration. However, a read can access a not yet migrated data at destination. So the destination-based protocol Rocksteady uses the priority pool to fetch the data from source to destination, and then let the client wait a while and try again. Then it can return the value. It can quickly shift the source node's pressure, and thus it has a shorter migration time. However, it can incur high query latency due to the missed data access in the destination. For example, it increases the medium latency from 100% to 400% compared with without migration. And that's the same reason it has the low throughput. Hybrid migration uses the both source and destination node to serve requests during migration. And it needs to keep the migration state somewhere. For example, Fuwa uses its client library to keep all the migrated keys, or it can be kept in the cluster coordinator. And Fuwa uses the destination to serve all the write requests during migration. And for the read request, based on the bookkeeping lookup, if this read accessing a key that has already been migrated, this read will go to the destination. And if this read access a key that is not being migrated, it may be in the source or on the fly. So Fuwa use the double read to query both source and the destination server, and then it merges the value with the latest version. It leverages both source and destination, so its query performance is better when most of the data is in the source. However, the double rate protocol incurs large bandwidth overhead between clients and servers, which is on average about 50% because it doesn't have a fine-grained state tracking. In summary, let's put this live migration protocol in the 2D dimension plane, and x-axis is the migration time, y-axis is query performance. Rocksteady has a short migration time but a low query performance. Source-based protocol has a high query performance but long migration time. And Fieldwell, the hybrid one, stands in the middle by utilizing both source and destination. We can see there's a fundamental trade-off between the query performance and the migration time. Thus, we propose the NetMigrate, and we aim to provide a better balance between these two angles. NetMigrate tries to minimize the query performance impact and incurring low extra overhead from migration. Also provides acceptable and tunable migration time. Existing solutions fall short to do so because they don't know where the data is and they pay the cost of going to the wrong places to fetch the correct value. So our key idea is to leverage the network-based solution, the top-of-rack programmable switch, to track the migration states. The advantage of the top-of-rack switch is it has a centralized view of all the data movement under the rack, and thus it can have the real-time information of who owns the data. Here's an example. If there's a query going from the slides to the top-of-rack switch, it will look up the migration state stored in the switch, and then switch can decide, based on the lookup result, the query should go to the source or should go to the destination. The enabler behind this is the switch's programmability. The programmable switch has a parser and the programmable packet processing pipeline, and it can process packet headers and packet customer fields at line rate without any performance loss. Also, it has an external register that can store the data. In NetMigrate, we use it to store the migration states. However, there are several challenges in designing NetMigrate. First is, how can we track the fine-grained migration states, given the on-switch resources are quite limited? And second is, how can we query during migration while maintaining strong data consistency? And third, how can we support dynamic migration policy? In the talk, we will focus on the first two challenges. And let's look at the first one. On-switch resources are very limited. For example, it only has 64 megabytes SRAM. So it's impossible for us to track every key value pair, whether they are migrated or not, because the number can be millions of. And key value store data structure usually has a hash table. So our idea is to combine the consecutive several entries in the hash table as a group, and we shrink the record granularity. We track the migration states in a coarser granularity at the group level. And given we track them at the group level, there are three possible states of a group. The entire group has been migrated, the group is ongoing migration, or the entire group is not migrated. Here's an example. Group 1 has 4 records, and at the beginning, they are all at the source, so they are not migrated. And then the migration starts. Some data migrated to destination or on the fly. The state is the group is ongoing migration. And finally, when all the data migrated to the destination, this group is migrated. Next is, how can we track the 3 group states? We use probabilistic data structures to track it here. We use Bloom filter to track the migrated groups, and use counting Bloom filters to track the ongoing migration groups. We need 2 data structures because one can only identify 2 states. And we use the counting Bloom filter to track ongoing migration groups because the ongoing migration is a dynamic process, and the counting Bloom filter's value can increase and decrease. Here's an example how this BF and CBF changes. At the beginning, all the BF and CBF at switch are initialized to 0, and the group is not migrated. And when the migration starts, the switch gets notified. This group starts migration, so CBF entry is set to 1. And when the migration moves on, all the entries in this group migrated to the destination. The switch also gets notified. The CBF is cleared, and BF is set to 1 to indicate this group has been migrated. And the second challenge, how can we query during the migration given our previous state tracking, while still maintaining the strong data consistency? And let's look at it one by one. First, we look at the not started migration state of a group. The client sends request to the switch. Based on the BF and the CBF lookup, they are both 0. The switch knows the entire group has not been migrated. So both read and write query should go to the source, and there's no consistency issue. And next case is when the group has finished the migration, BF is 1 and CBF is 0. Switch knows this group are all at the destination, so read and write should go to the destination. However, when the group is ongoing migration, there can be inconsistency example if we don't carefully design the query protocol. When the query arrives at the switch, for example, if the write goes to the destination, and it can update a not yet migrated field. And then later, if a read accessing the same key, the switch directs it to the source, the read will access the stale value. Then the query result is inconsistent. During the ongoing migration period, switch is unsure about whether the accessor key is where the accessor key is located because it only tracks at the group level, not the key level. And also, it's unsure whether there's a write before because the switch resources is limited and it cannot track every write. So NetMigrate does this. For all the write query, it routes to the destination. And for the read query, targeting this group, it will do the double read, query both server, and merge with the latest value. Here, data consistency is maintained by the double read, and the overhead caused by double read is negligible because a group ongoing migration period will be short. This is unlike the fewer that they use double read over the entire migration period. However, the false positive of BF and CBF can still cause the inconsistency. For example, the BF we see are 1 here, but actually they are updated due to the hash collision. And the switch decides to route read and write to the destination. But this read can access a not yet migrated data. So to correct this, we use priority pool to fetch the data from source to destination, and then return the value to the client. The overhead from this false positive is negligible because the error is bounded. And CBF can also have false positives. Please check more details in our paper. Putting it together, NetMigrate leverages the probabilistic data structures on switch data plane to track 3 migration states. And we carefully design a query protocol to guarantee the consistency. The overhead caused by false positives and the unsure states is small. In evaluation, we evaluated NetMigrate on a testbed consisting of an Intel Tofino switch connecting 3 commodity servers. And we compare NetMigrate with 3 baselines, the source-based migration protocol, Rocksteady, and FUA. And all of them migrate 256 million key-value pairs from source to the destination node. And each key-value pair has 4-byte key and 64-byte value. We tested on the YCSB workloads with varied write ratio, and we also changed the source CPU budgets to mimic the load imbalancing scenario. And here in the talk, I will show you the YCSB with 5% write ratio, and the source is not overloaded with 4 CPU budgets, and comparing the NetMigrate with the source-based migration protocol. The source migration protocol has a slightly lower throughput during the migration compared before and after the migration. And NetMigrate has an on average higher throughput compared with before and after migration. And we see there's a performance peak here because before that, the throughput comes from the source node and the destinations. And when more and more data are moved to the destination can serve more requests, so the throughput increase. And after that, destination is serving more requests because more data are in the destination. And also there's the migration insertion query in destination. So the performance drops. And NetMigrate can achieve from 32% to 78% average throughput improvement compared with the source-based Rocksteady and Fuwa, when we limit the NetMigrate to have the similar migration time compared with each of them. And source protocol has a slightly higher medium latency during migration, while NetMigrate has an on average lower latency, medium latency, because both source and the destination, they all serve the request, and they can share the query pressure. NetMigrate can reduce the medium latency from 49% to 65%, and it can reduce up to 39% average tail latency. Also, it's compared with the three baselines. Let's look at the network overhead. We divide the overhead between the client side, which is between client and servers, and the server side, which is between the two servers. Rocksteady only has the client-side overhead, which is about 10%. And source-based protocol has server-side overhead, and it's proportional to the write ratio. Fuwa has about 50% client-side overhead. Although NetMigrate has both of them, these overheads are both negligible. In conclusion, existing key-value store migration techniques still suffer from low query solving performance and high overhead. We propose NetMigrate, a network-based hybrid live migration approach. It tracks the fine-grained migration states in programmable data plane and can provide enhanced throughput and low migration overheads. We open source NetMigrate at this GitHub repo. And thanks, I'm happy to take any questions.